Now coming to case z and case x mask in the case expression. So the masked bit can be specified on either side of the case statement comparison. Verilog case z and case x statements allow bit to be masked out from the case expression. So masked bit can be specified on either side of the case statement comparison. So they are trying to say this is a problem. Okay, they're telling that masked bit can be specified on either side of a case statement comparison. Now we'll see what is the problem here. Verilog case z and case x statement allow bit to be masked out from the case comparison. So if you want to mask some bits which you do not want to compare at all, so in that case you can mask those things. So with case z, any bit set to z or question are masked out. So any bit in case z, either if that is z or comma are masked out. So with case x, any bit x, z or question mark are masked out. So in case z and case x, only difference is even in case x it will take x as a mask, and in case z it will take z and question mark as a mask only. So these constructs are useful for concisely modeling many type of hardware as well as verification code. Now we'll see one example. We will see one example of wildcard case x. Always underscore com begin case x instruction. Okay, so in instruction 4 tick b question. So opcode is instant 2:0, only test upper bit. Okay, if 4 tick b 100 opcode is 3 tick b 001. If then after that you have decoded some other information. At last default begin $display error invalid instruction, opcode is 3 tick b xx. So in the preceding example, the mask bit are set in the first case item. So you are not bothering about these bits. So you have masked this bit. Okay. The intent is that if leftmost bit of the instruction is 0, the other bit do not need to be evaluated. So first your simulator will see this bit, that is MSB bit. If it is 0, your simulator will not see any other thing. Okay, it will not evaluate other bits. So directly it will evaluate this opcode equal to instruction 2:0. After all possible valid instruction has been decoded, a default branch is used to trap a design problem. So they are telling that even so if you see in this example, the mask bits are set in the first case. So we have masked the other bits, means whatever may be the value of this bit, it will your simulator will first see this 0. If 0 is there, it will execute this instruction. So this is the use of case expression. So after all possible valid instruction has been decoded, a default branch is used to trap a design problem should an invalid instruction occur. So you have seen one default statement they have kept at last. Okay, this default statement will help us to come out from traps. Okay, come out of traps means suppose you have gone into some default state. Okay, where you some default state. So how you will come to know? During that time opcode is 3 tick bxx. So this by seeing opcode as 3 tick bxx, you will come to know, yeah, that your state machine is going to some unknown state. Okay, so during that time you can easily recover that thing. So what else branch will be taken if there is a design problem and instruction has been 4 tick bxx? The intuitive answer is the default branch will be taken and an invalid instruction will be operated. If you are getting if instruction equal to 4 tick bxx, in that case default statement will execute because it will not match with any other any of the possible combination which they have mentioned above. Okay, so this is a problem. Okay, so the case x and case z statement allow the mask bits to be set on the either side of the comparison. Okay, in the preceding example, if the instruction has a value of 4 tick xbxxx or 4 tick bzz, all the bits are masked from the comparison, which means that first